Welcome back. So we were discussing maximum a posteriori estimation. Okay, we'll continue to do that. Okay, all right. Okay, and what we are doing to, we are going to choose is a, what you are trying to do is a will to have mean for an univariate Gaussian. Excuse me. I choose this because I have already shown you the mean for an univariate Gaussian for the MLE, right? So I just want to do the same calculation again. I mean, not same, but just to show the relationship. So the problem statement is I have theta is a random variable. Okay. All right. Which is, sampled from a normal density function with some constant variance. Okay. And some prior mean. So this is nothing but a prior mean. All right. And my data is this, and we also assume that this is IID, independent and identically distributed. Okay. All right. Therefore, I mean, I will assume that. So these are standard. What I know is the maximum a posteriori estimate or map is nothing but finding the maximum on this, right? And this is nothing but what? I mean, from a Bayesian standpoint, correct? Okay. Okay. Now the denominator doesn't really matter. Okay, so denominator doesn't really matter because it's constant, right? I mean, it's on the given data. So I mean, this is equivalent to writing, and since we are using a standard normal, I mean, I can just, instead of looking at the likelihood of the original likelihood function, I can just take the look at the likelihood of the log likelihood function, right? Okay, so I'll just rewrite this as. Okay. All right. Now, I mean, you see two parts here. I mean, as we know, this part right here comes from MLE. And we already have done the calculation for that, right? I mean, so I'm not going to repeat it. I'm just going to copy that calculation. The extra part is this because of the prior, right? Okay. So if we do the maximum a posteriori, it is the same, finding out the partial derivative of. Now this part, we're doing MLE for the mean only, right? Okay, so we are just, MLE for the mean of an univariate Gaussian, right? So this part is already done, and what I know is that I can simply write this, copy this from the previous calculation. It's I equal to 1 to n xi minus n theta equal to 0. Okay. Right. So what I should be focusing on is this part, right? So del theta of ln of p theta. Okay. Now this is equivalent to, since I know that data is sampled from a normal density function with constant variance, and that constant variance is 1, right? So instead of sigma, I just plug in 1, okay? And my likelihood function is just this, all right? Now we do this, it's pretty simple, right? I mean, if I do this, I'll have, del theta of minus 1/2 ln of 2 pi minus 1/2 theta minus mu square. Okay. All right. Now, I mean, the first part I should not really bother. I mean, what I should be doing with the second part is, this is nothing but, I have a 2 times theta minus mu cancels out with a 2. So theta minus mu with a negative sign. So it's just mu minus theta, right? So I have this expression from the first part, from the likelihood function part, and I have the second one from the likelihood part, right? I mean, from the prior part, sorry. So if I combine what I have now, because I have to have this del theta of this whole thing, I have to set this guy to 0, right, in order for the maximum estimation. So what I have is, if I simplify this further, I will have this n plus 1 over sigma square, right, times theta, because there is this n theta over sigma square, the plus 1 comes from the other part, right, okay, alright, and set this equal to 1 over sigma square summation I equal to 1 to n xi, right, plus the mu comes from here, okay, as simple as that, okay, alright, okay. Now continuing further, what I can do is I can just rewrite this, because this now becomes your maximum a posteriori estimation, okay, theta map, and I can simply do this just transposing this. I mean, I can multiply this both sides with sigma square and divide by n plus 1. If I do that, I'll have an n plus 1 times mu over sigma square, right, okay. So what I'll have is, I'll have 1 over sigma square summation I equal to 1 to n xi plus mu divided by n over sigma square plus 1, okay. So this is n plus sigma square multiplied over sigma square, right, and so I can simplify this as sigma xi I equal to 1 to n plus mu sigma square divided by n plus sigma square, okay, alright. Now we'll do a clever trick here. I mean, just look at this carefully, okay. Now the coefficient of this first term is 1, but I can write 1 as n times 1 over n, okay, right, and if I do that, what I'll get is, I mean, and then, I mean, why I did this, it's because, see, this now, once I do this, let's look at this carefully, okay. What is this? This is the summation of all observation points, all over n observation points divided by the number of observations, right, okay. So what is this? This is sample mean, isn't it? What is this? Sample variance, right, okay, alright, good. So I can replace this by the sample mean x bar, right, okay, and so let's copy this down, because this is the key expression. So let me go to the next one and just copy this down. So remember, so we are doing this theta map, right? So what I have here is n over n plus sigma square, and then I had this summation I is equal to 1 to n xi, right, which is nothing but the sample mean, okay, and then the other term was sigma square, right. Remember, we had n plus sigma square, and the denominator is sort of times mu. Okay, great. So there is this, what is this mu? The mu is prior mean, right? What is this guy? This is sample mean, right? Okay. Now, what do you see here? You see that the maximum a posteriori estimate for the parameter theta, right, is a combination of sample mean and prior mean. That is great, right? Because what this will happen is, I mean, you are not dominated by the sample mean only. The sample mean comes from your observations, right? As and when you get data and you keep on getting data, right? I mean, so the first term will change, right? But I mean, if this second term is absent, you simply have a maximum likelihood estimate. Do you see that? Okay, we'll come back to this later on, right? But as of now, we also observe one thing. This is n over n plus sigma square, and this is sigma square over n plus sigma square. If I take the sum of the two, I get 1. So what I have here is nothing but a convex combination prior mean. Okay, all right. Now each one of these guys can be upper bounded by 1, right? Okay, so the maximum that they can take is 1. I mean, it's very likely that they are both less than 1, right? Okay, so this is really a convex combination. So I mean, just to recall, a convex combination of x and y is sort of written as alpha x plus 1 minus alpha y, where alpha is between 0 and 1, right? Okay, all right. And what it does is basically gives you a line segment between x and y for all possible combinations of alpha. Okay, now what you can see here is that if alpha is 0, then all you get is 1 minus 0 is y. So if alpha is 0, you get y, and if alpha is 1, you get x. For all the intermediate values of alpha, you get a line segment. Okay, so we can just use this to interpret this. So let's come back to this. When sigma square is 0, your theta map becomes just a sample mean. Okay, all right. So what does it mean for the sigma squared to be equal to 0? That means you have no variance. Okay, all right. So absolutely no variance. So your theta map is just sample mean. So when you have no variance in data, then you are actually not bothered about overfitting at all, right? Okay, and so what you can say that when you have no variance, I mean, I think it is just MLE is good enough, right? I mean, that's what it says. When you have no variance, you are not bothered about, incorporating prior. So your theta map is just the MLE. So in this case, MLE is a special case. All right. But as n and sigma square, I mean, the number of observations, if you increase the number of observations, decrease the number of observations, as the number of observations and the variance both change, you will see, your map estimates will change, right? So for us, let's say now, I mean, if you think of, a classification problem and you have like more than one different posterior estimates, okay, for the same data. Okay, so these posterior estimates can be, theta is a hypothesis, right? So your posterior estimates can be linked to your hypothesis or class level. So let's say you have two class levels, right? Positive and negative. And you are computing as and when data comes in, you are computing the map for the positive class level given data, you are computing the map for negative class level given data, and just use the one which has the higher value, right? Okay, so that's convenient. Okay, now the other thing is when you have n equal to 0, meaning you don't have data. I mean, there is no new data, right? So n equal to 0 means there is no data. Okay, so in that case, what will happen is this guy, the first term, will vanish. Okay, and your theta map then will be purely depending on the prior mean. So if you have no data, all you can do is to do an estimation based on your prior knowledge. Okay, and that's what you do. Okay, all right. Also, when your n goes to infinity, meaning you have lots of data, large amount of data, right? Then what happens? When you have large amount of data, then the second term will become 0. Okay, all right. And the first term, it's easy to see. I mean, take the limit as n goes to infinity, right? So in that case, your theta map is just x bar, purely x bar, which is the sample mean. Okay, all right. So for a large amount of data, maximum a posteriori estimate is as good as the sample mean, right? I mean there is, which is MLE. Okay, so that's why I said, if you recall, that when you have large amounts of data, you probably don't care about the prior information at all. Okay, so you just do the MLE and be happy with it. Okay, all right. So what are we going to do? Generally speaking, what are the practice norms? Just to summarize, what are the practice norms? In practice, I mean, in the absence of prior, if there is no prior, right? In the absence of prior, just use MLE. If you don't have prior, you can't do anything about it, right? Okay. And in the case of a flat prior meaning there is no variance in the data, right? In the case of a flat prior also, you really don't need to care about the overfitting, right? Your map is equivalent to MLE. Okay, all right. Use MLE and in the absence of data, all right. So roughly speaking, this is what we wanted to cover as far as maximum likelihood estimation and maximum a priori posteriori estimation is concerned, right? Okay. And this kind of estimation you can also see in naive Bayes. Okay, all right. Now the next topic would be something that will once again be some sort of an interpretation from MLE, which is a clustering technique, and we'll come back to that in a moment. Okay.